the situation that we were talking about yesterday, but instead of doing this with numbers, I want to just show you something. And it only works out this way for this one kind of problem. And for some of you, this might be a lot of alphabet soup on the board. But let's just say we're going to launch something at an angle with an initial velocity of VL for the launch velocity. Okay? I want to find out where it lands. But I'm not going to give you any numbers. I want to see if we can come up with a generalized relationship for where this lands. So we're going to start with our mnemonic here, our organizational principle. And we'll have all the things that we would normally place here, except we have no numbers. So instead of numbers, I want to place what I feel are appropriate placeholders here. I'm going to go through our set of steps that we've done. And again, our goal is to produce a generalized response or a generalized relationship. So this problem has at least one zero that we're familiar with. If you're launching from the ground and it's landing on the ground, then we know delta y is going to be 0. Now, that should send up, it probably doesn't because you guys don't know what to be worried about, but that should send up a warning. That means that whatever we derive from here will only work under this circumstance. If you apply it to another circumstance, it won't work. So before we go any further, make sure you highlight that and indicate we're going to derive something, but we're predicating it on the idea that delta y is 0. So if you have any other situation where delta y isn't 0, what we're going to see doesn't work. And to be frank, so we know a little bit about the initial launch velocity. We know we have VL at some angle, but we also know that means this is VL sine theta, and this is VL cosine theta. That's because when we take our velocity and we break it up into components, there's a horizontal component and a vertical component. And I keep drawing this just to remind you that those things are true. Acceleration is going to be gravity, so I'm just going to put g here. And after I've acquired all the things I think can be placed here, I'm going to stop before I get any further and try and pick what I feel is an appropriate direction for positive and negative. Doesn't matter what we choose here, so do you guys want up to be positive or up to be negative? All right, so we'll make up positive. That means I have to make this negative. I'm going to put an intentional negative sign there because gravity is downwards. Now, in the past, we've had numbers for this, but there's no numbers here. Our goal is to come up with an expression for the time. And once we have an expression for the time, we'll use it over here. So I'm going to start with delta y equals 1/2 at squared plus vy naught times t. Again, it has the things in it that we have placed here and does not have final velocity in it because we don't have anything to put in for final velocity. I'm going to put my 0 in. This is 1/2 times negative g t squared plus VL sine theta all times t. Now that's a lot. A lot of students start getting freaked out when they start seeing this, but this is just an expression and we want to solve it for t. You do that part. Have something in this. Wake up a little bit and be a part of what's happening. So I'll call on one of you, or I'll just walk around and see if you can isolate t here. If you're trying to isolate t, then you want to probably factor out a t first, because this is a quadratic. You want to factor out a t. That's going to leave me this negative 1/2 gt plus VL sine theta. So we factored out 1t. And we don't throw it away because t could be 0, so we just factor it out and set it equal to 0. And then we set everything in parentheses equal to 0. Just because there's no numbers doesn't mean you can't still perform. It's algebra. The whole point of algebra was to be able to come up with generalized expressions and not have to have specific numbers. I already saw two of you put in 10 for G. Well, now you've forced it to be on the earth. Perhaps leave the G in there, right? The whole idea is to remove the numbers so that you can use it in any generalized way. So don't put a 10 in for G if you're trying to come up with a generalized relationship. I don't want to do all these other steps. I'm going to have to because of 3 students I saw. I have no idea what we're doing. So I am going to do a couple extra steps. I'm going to move this term to the other side because it's the negative term. That's not necessarily a solid reason, but it's the reason I'm going to use for moving that term over. I want to get t by itself, so I'll multiply both sides by 2. And now I'll divide both sides by g. And I'll get t equals 2VL sine theta over g. This is a generalized answer for t. And actually, although it's general, it works only in this circumstance. And this is a circumstance we created for this to work, but it assumed delta y equaled 0. So it won't work in any other circumstance. It will only work in this one, which I'm going to keep re-saying because I'm pretty sure I'm going to see something on Wednesday that's going to disagree with this. So I'm telling you right now, this only works when delta y is 0. But now, again, our goal is to come up with the range, and the range is to take delta x, multiply by vx and t. That'll give us the range. So this is my delta x, this is my t. So let's bring them together, and I'll get delta x equals VL cosine theta times 2VL sine theta over g. That looks a little messy. I'm going to clean it up a little bit. And what I mean by clean it up, I'm going to put this on top of the fraction. So, and because that's algebraically correct. I know some of you don't have a hard time with that, but this is just VL cosine theta over 1. So now I multiply the top of the fractions together and the bottom of the fractions together. And that's going to give me 2VL squared sine theta cosine theta all over g. Now I'd say we stop here, except I know things. Some of you know things, but I know things. Right now, this is an okay relationship, but it really hasn't saved us any time, and we really don't get anything new from this. It's not like we can solve this for theta the way it is, because we can't isolate theta because it's in 2 different trig functions. But one of the powers of trig is the idea that there are what's called trig identities. You guys ever heard of trig identities? That's not very many of you, and that's okay. I'm going to put a few trig identities here. These are actually going to be on your equation sheet, which suggest that the AP folks believe you might need them. A trig identity allows you to replace one trig function with another. There's a bunch of them. I mean, there's quite literally books filled with them. So there's a lot of trig identities. An easy one is this one, sine theta over cosine theta, because that's tangent theta. That one's easy to understand because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. And here, the 2 hypotenuses would cancel and give you opposite over adjacent. So it's kind of easy to see where that one comes from, isn't it? But there are a few others that are less easy to see. Like this one, sine squared theta plus cosine squared theta equals 1. Have you guys seen this one before? Do you understand that this is just a Pythagorean theorem? If not, opposite over hypotenuse squared plus adjacent over hypotenuse squared equals 1. Wouldn't you agree? So multiply through by hypotenuse squared, and we get opposite squared plus adjacent squared equals hypotenuse squared. Right, just a Pythagorean theorem. So far these haven't been particularly interesting, but there are a few that are a little more interesting. This one you've probably never seen before. At least my experience is that there's only a small number of people in the room who have seen it. How many of you have seen the double angle formulas? Well, there's a bunch then. So you know about things like sine of A plus B. You seen this one? So you know that's going to be equal to sine A cosine B plus sine B cosine A. If you didn't know this, you know it now. There's no excuse for you not knowing it. Again, there's a few things I can't stand, but intentional ignorance is not one I will tolerate. So you now know this, right? It's in your notes. You have a list running of trig identities that you could use. And if you don't understand that I'm doing this for your benefit, then you'll need to step up. Now, the interesting thing that happens here is if you change this to sine A plus A, because this part looks very silly, right? Because all of it's A now, and those two terms are the same. So this will be 2 sine A cosine A, but the left side will be sine of 2A. Do you see where that could be used? Because I clearly see where that could be used. So I'm going to use a trig identity. I'm going to replace 2 sine theta cosine theta with sine of 2 theta. The power of that trig identity means that I've now changed this to something that I could actually use if I wanted to solve for theta. What angle would I have to kick the ball so that I could make the goal, stuff like that. Now this is called the range equation, which is too bad because it doesn't solve very many range equation problems. It only solves problems where delta y equals 0. And I have to keep hammering that home because there's like 3 of you who really don't listen very closely. And so you make mistakes like this and you look silly. You'll turn it in tomorrow in your quiz and go, I don't know how I got it wrong. Well, I'm telling you, this is why you got it wrong. But I want to use this as a speaking point to explain something. So we all together on this? We're up to here? Yesterday we did a question, right? I threw down one. It was not particularly hard. I think it was, the ball was kicked at, was it 25 meters per second at an angle of 15 degrees? Can't quite remember. Yeah. 25 meters per second and 15 degrees. So let's consider that problem again, this time using the range equation. So kick the ball 25 meters per second at 15 degrees. Once I realize that this is going to be a problem where delta y equals 0, and I decide to use the range equation, I can step right to the answer by just using the range equation, which said take the velocity, square it, then multiply by the sine of 2 times the angle, so 2 times 15, and then divide by whatever the acceleration of gravity is at that location. I see people reaching for their calculators, but come on, folks. 25 squared is 625. Divided by 10 is going to be 62.5. It's good to be able to know things, and 25 squared is something worth knowing. Sine of 2 times 15 is a sine of 30. What's the sine of 30? Don't you have this one ready to go? You should probably start learning the 30, 60, 90s, because sine of 30 is 1/2. That's why I gave it to you, which makes this 31.25 meters, just like yesterday. Now here's the problem. You guys are aware of some things, but not aware of others. And it's remarkable, the things that I say that don't you know this, and you guys just sit there stoically as if, I expect you to. Do you guys know where sine is positive? Can you tell me that? Just curious. Go ahead. Okay, it's positive in quadrants 1 and 2. That's right. This is because if I have an angle measured from the x-axis in this direction, the opposite side will be positive. And if I have an angle, say over here, measured from this direction, the opposite side is still positive, even if the adjacent side is negative. So we say that sine is positive in quadrant 1 and quadrant 2. Now, I wouldn't normally care about an angle over here. If I'm trying to throw the ball this way, I wouldn't think throwing it this way would ever really work, would you? Doesn't make any sense. But remember, this formula has a 2 theta in it, which means I have to divide these angles by 2. So this is why 15 degrees and 75 degrees works. They're complementary angles. Let me give you an example. Let me show you why this would be the way it is. What if, instead, we didn't want to hit a point that was 31.25 meters away, but instead we wanted to hit something that was 40 meters away? I can still only kick at 25 meters per second, but I want the ball to go 40 meters away. What angle would I have to do for that? This is a problem that is unsolvable using this. Unsolvable using this. Only solvable using the range equation, which means I will only ask it in situations where delta y is 0. But knowing that, I can use the range equation here to figure out the answer. Again, my range is going to be 40. My launch velocity is still 25. So now I can begin the work. I multiply both sides by 10. Divide both sides by 625. Before you go any further, warning, if the top number is ever bigger than the bottom number, if that should happen, then you know there is no angle that will hit that target. So right away, you have a way of knowing if you can even hit the target. If the top number is ever bigger than the bottom number, there is no angle that'll work, right? Because the sign doesn't ever get bigger than 1. But this one works. This one fits in our middle category. And if I do my 400 divided by 625, and hit my inverse sine, I find I get 39.79. So sine of 2 theta equals 39.79. This is not my launch angle. Oh, not the sine of 2 theta. 2 theta is equal to 39.79. Again, this isn't my launch angle. This is 2 times my launch angle. My actual launch angle is going to be half of that. But like I said, sine is positive in the first and the second quadrant. So if I take my 39.79 and subtract it from 180, I'll get 140. Again, you look at a protractor. If 0 is that way, 140 is that way. So if I'm trying to hit something over there, I would normally not care about angles that go that way. Would that make sense? But that's not the case here. I have to divide by 2. And the moment I divide by 2, I get that theta equals, 20 and 70. Both of those are this way. So there's always 2 angles whenever we have a delta y of 0, the high angle and the low angle. The low angle gets it there sooner. The horizontal velocity is greater and the y velocity is smaller. So the low angle gets it there sooner. The high angle takes a long time. Of just showing you the basics. It's when we have to get outside the basics that you're probably going to start running into some trouble. And some of your homework does run outside the basics. But this question is still just the basics. I'm going to call this a type 3 problem, mostly because there's just no shortcut here. And you'll understand what I mean by no shortcut in a minute. Let's put the 25 meters per second and 15 degrees up at the top of some rooftop that's now 15 meters above the ground. So we'll combine our two problems. And I want to know where this ball lands. I have nothing new to teach you for this, so you should just try it, solve for the time, and figure out the range. But you'll understand why this problem introduces a new level of difficulty. It's not any different. You still use this little tactic here, but see if you can figure out why this problem has a new level of difficulty. All right, so I'm hopeful. We have a delta y equal to, say, negative 15 meters, a vy naught equal to 25 sine 15. Don't know what vy is, but our acceleration, negative 10 meters per second squared. That work out for all of you? Put all the things where they're supposed to go. And we're looking for delta x, but Vx is going to be 25 cosine 15. So we need t. You guys see why there's an issue, right? You have to do the full quadratic now. So negative 15 equals 1/2 times negative 10 t squared plus 25 sine 15 times t. You're going to get 2 times if you use the quadratic formula. Don't throw away the 2 answers. Keep them. I got 2.5, and I got negative 1.2. You guys get something near that? Now, if you get a negative time, that one's not going to be useful. So probably don't worry about it. The positive time is the one you probably want. And once you have your positive time, put it here. But what if you were trying to do this? Or what if I wanted to go from someplace low to someplace high? And you were working this problem. This expression is giving you the time when the object is 15 meters below you. Well, you saw the way I drew it. There was only one time when you could ever get 15 meters below, because you started up here, went up first, and then down. But if you're going from the ground upwards 15 meters, you realize you passed the 15-meter mark twice. Once while the ball is going up, once while the ball is coming down, which means these two would be positive. You'd have to figure out which one of those you need. Do you want the one when the ball is on its way up, or do you want the one when the ball is on its way down? So always check out both routes, because there might be a real meaning to both of them. And I actually have, I think, a question in the homework that does exploit this a little bit, just so you guys can check it out. All right.